everyone, my name is Fabio, and today I'm going to talk about one of the chapters of my thesis that I did at University of Tasmania, and the topic is in the ocean heat storage driven by redistribution of heat in response to ocean circulation changes. So the main motivation for this work is a large spread in thermosteric level projections. You can see in the figure here to the right, there's very large standard deviation in dynamics level at mid and high latitudes of both hemispheres. And part of this spread is caused by the climate sensitivity, or how the atmosphere responds to changing radiative forcing, and part is caused by how the ocean responds to those changes. And in terms of the ocean response, there's a large variation in the ocean heat efficiency uh, among different CMIP models, and that's partially caused by the differences in vertical heat transport and the process that cause this heat transport. So it's important for us to understand the process behind vertical heat transport and how they differ between different models. And the Flux-Anomaly-Forced Model Intercomparison Project, the FAFMIP, aims to isolate the ocean response of this uncertainty by obtaining surface heat, freshwater, and momentum flux perturbations from an ensemble mean CMIP5 models under double CO2 scenario, and force individual CMIP6 models with the same perturbation. And one good advance that you're going to have in CMIP6 is the inclusion of this process-based diagnostic, which allow us to decompose changes in ocean heat and salt content into the contributions from individual physical process. And another important feature that you have in FAFMIP is the inclusion of two tracers, the added heat TA and the redistributed heat TR, which allow us to decompose the change in ocean heat content into these added and redistribution components. So the added heat evolves just respond to the change in the surface heat flux, while all of the change in added heat will be just because you are applying this heat flux perturbation at the surface, while the redistributed heat will not feel the heat flux perturbation, but only feels the climatological surface heat flux. So it will evolve and transport the heat reservoir just because of the change in the ocean circulation and diffusion. And importantly, the redistributed heat provides the surface temperature for the calculations of this air-sea fluxes. So this redistributed heat tracer includes also the redistribution feedback. So when you integrate it globally, the redistributed heat is not zero because it also includes the feedback that it has in the surface heat fluxes. And in terms of the previous studies of ocean heat transfer processes, most of them have found that the global balance in a steady state is between the mean advection moving heat downward and the eddy-induced transport moving heat upward, where the eddy-induced transport accounts for both the eddy advection or GM parameterization and the eddy diffusion or isoneutral diffusion, usually parameterized to the redi diffusion. And while these two main processes are mostly constant with depth, so they have the same signal from subsurface to the deep ocean, another framework has suggests the combination or the superposition of the advection and eddy transport into a single process called the super-residual transport, the SRT. And here in the zonal integrated budgets, here the figures in the bottom, you can see that the SRT, in opposed to this same signal that advection and eddy transport holds at different depths, the SRT has two different regimes. One at deep mix layers where it warms, and another one below those mix layers, the ocean interior, where it has a cooling effect. And I like to summarize the super-residual framework into these two regimes because it has a clear effect on the formation and recirculation of dense water masses. So in the deep mixed layers, the super-residual transport counterbalances the vertical mixing process, which basically cool these mixed layers while they form dense waters. And in the ocean interior, the balance is between super-residual transport and dineutral mixing, which is much more like the classical advective diffusive balance if you consider the SRT as the advective component. So for this study, we use the XS OM2, it's an ocean-only model with a 1 degree configuration. It's spun up for 1,000 years, so it's pretty much in steady state using the GRA 55 repeat year forcing. And then you perturb this model with the FAFMIP flux anomalies for another 8 years. So importantly, because ocean-only models usually has to apply the surface salinity restoring, we have to perform two different control runs so you can apply the freshwater perturbation in a clear way. So in the first control run, you just kept the same salinity restoring as usual, but you saved salt flux from restoring every 6 hours. And then performing a new control run, we deactivated the salinity restoring, but we apply that saved salt fluxes, which allows the model to behave in a similar way, but without having to the restoring interfering in the freshwater surface perturbation. So jump to the results. In terms of the vertically integrated ocean heat content, here you have in the top the total heat content chains, in the middle the added heat, and in the bottom the redistributed heat. We can see that the most of the heat is stored in the Atlantic Ocean, so it's larger than other basins, and the Pacific or the added heat is mostly found at mid and high latitudes, but especially in the North Atlantic and in the Arctic, while the redistribution has important warming or heat storage at low latitudes, especially in the Atlantic and Pacific basin, but it also has a significant contribution along with the ACC and in the path of the Gulf Stream. And our main objective for this work was to investigate the mechanism of the redistribution warming at low latitudes and along with the ACC, given that the North Atlantic effect of the heat redistribution has been fairly investigated before. So analyzing the heat budget for the added heat tracer. So here in the top you have the heat flux perturbation from FAFMIP. We can see that in terms of processes, most of the heat flux perturbation affects the vertical mixing process, such as the dineutral diffusion, the non-local KPP, and convection terms, which those terms at the mean state, they mostly cool the mixer layers, and because we are applying this positive anomaly at the mid and high latitudes, this vertical mixing process decreases its cooling effect and cause local warming, which is locally balanced by the super-residual transport, which transport part of these heat anomalies equatorward. And looking at the zonal integrated budget, here I'm showing the Atlantic Ocean basin. It's much clear. It is even clearer that the vertical mixing process in the right are mostly warming the mixer layer depths, and the super-residual transport has this secondary effect which removes heat from mixer layers and transport it down and equatorward along the ventilation pathways. And when you look at the heat budget for the redistributed heat, instead of having this strong effect from vertical mixing causing the heat storage, actually the redistribution of heat is much more dominated by the super-residual transport, with minor effect from the vertical mixing process chains. So basically the tropical warming and the warming along the northern boundary of the ACC is caused by changes in the ISRT or changes related with the large scale circulation and mesoscale eddies. And it's important also to highlight here that the warming caused by the SRT modify, of course, the surface sea surface temperature, and that imprints this redistribution feedback in the surface heat fluxes. So where the ocean gets warmer because of the heat storage, the ocean loses heat to the atmosphere. Even though that this is an ocean only model, it has this redistribution feedback effect. And look at the zonal perspective. It's also clear that the net tendency of the redistributed heat storage is much dominated by the super-residual transport. And vertical mixing process have only a minor contribution. So then we investigate further the mechanism of the heat redistribution. So if you look at the left plot, the meridional heat transport due to the super-residual transport, you can separate the change in the north and southern hemisphere, and that are dominated by the effects in the Atlantic basin. So in the northern hemisphere, we have a decrease of the polar heat transport, which when you look at the maps of vertical heat convergence in the upper 1,000 meters, you see that there is a decrease in the heat transport along the Gulf Stream, the North Brazil Current, and Guyana currents. But there is also an increase in the transport along the eastern boundary and equatorial currents. So that is how the heat is redistributed from the subtropical gyres to the equatorial regions, so causing this tropical warming. And when you look at the southern hemisphere, we actually have an increase in the polar heat transport, which is mostly dominated by this strong intensification of the Brazil current in the South Atlantic. So because the Brazil current intensifies at the surface and subsurface, it increases the heat convergence in the subtropical front in the South Atlantic, and part of this heat is bring it back to the tropical ocean via an also intensified Benguela current, the eastern boundary current in the South Atlantic. So change in the South Atlantic causes partially this tropical warming, but also contributes to the increased heat convergence in the subtropical front. And last thing, you analyze the change in the ocean, upper ocean stratification, and you could see that regions where you have most of the subtropical gyres, they have increased stratification, and because of that, we increase the barrier between the surface and lower thermocline circulation. So basically, most of the subtropical gyres, besides the South Atlantic, it increases the surface circulation, or the western and eastern boundary currents, but it decreases the circulation at the lower thermocline. And because the eastern boundary currents are much shallower than the western boundary currents, that's how the mechanism of heat redistribution is done. So the eastern boundary have a main effect in bring heat back to the tropical. And in the South Atlantic, where a lot of heat is stored, you can see that the stratification actually decreases, and also along the subtropical front. So regions where you have heat storage due to redistribution, the stratification, the upper ocean stratification decreases. And just to summarize the results, so we highlight the importance of heat redistribution for the change in ocean heat content. So it is the main mechanism of tropical warming, responsible for 65% of the change in ocean heat content, and the the tropical warming results in this strong redistribution feedback at low latitudes. And redistribution is also contributes significantly to the heat storage at the mid-latitude Southern Ocean, around 25%, which is aligned with some of the recent studies. And in terms of the redistribution, it is largely dominated by chains in super-residual transport, so large scale and massive scale chains in heat transport, and that goes around this interplay between chains in western and eastern boundary currents and equatorial currents that leads to heat transport towards the equator and also strengthening of the heat convergence at the subtropical front. Thank you.